Hello, everyone. Good afternoon. We have a lot to cover today, so let's get right into it. So first of all, let's level set. What is DoubleZero? So DoubleZero is the protocol. We're building a protocol at Malbec Labs. And the protocol is a thing that we've been working on since the white paper was created last December. And the realization of the protocol is what we've all come to know and love, which is the high-performance, decentralized global network. And what I want to stop here and focus on decentralization for a second. So this is something that has been really dear to my heart since I was a teenager working with Linux and being anti-Microsoft and all these kind of things. And this also flies in the face of basically everything that's happened over the last 20 to 30 years in terms of consolidation, in terms of monopolization and conglomeration. And so this also provides different incentives and means that we can build things together that we couldn't build alone. Now, let's take a look at a high level of what the DoubleZero architecture looks like. So we have in the middle the protocol, and we've highlighted two bits here, serviceability and telemetry. So the serviceability program basically defines what the network is. The locations, the exchanges, the links, the latencies, the jitter, the bandwidth, and so on. And the telemetry is we pull data from our private network or from the collective's private network, and then we also compare our private network against the public internet, and this is how rewards are generated for the network contributors. And all this data is on-chain. We have our own DZ ledger. Anyone can read it and see the data that we have, and we also expose this in public metrics on our site. Now, on the left, we have tenants, which implies that there's more than one tenant, or can be. Our first tenant is Solana, and our primary users are validators. And we have about 40% of validators on the network. Now, on the reward side, what I want to highlight really quickly is that we use Shapley values to calculate rewards. And Shapley values essentially drive the quality up. So the way we measure it is if you're not part of the network, how much worse is the network? And this is really important because the ISPs have a race to the bottom. We have a race to the top. Quality generates quality. Now, let's talk about what high performance is. So we always talk about reducing latency. But that's not enough, right? Latency without control, you get a lot of jitter, and it makes predictions that much harder to guess. So performance is speed and control. And so we've launched mainnet beta in October, and we have some interesting data to show. And now I'm going to show something from an RPC provider here, and we're going to take a moment on this slide. So here on the y-axis, we have the RTT time in seconds, and then on the x-axis, we have the date, or the time that has transpired. And on the left, you can see this is on the public internet. The middle, the DoubleZero difference, is in the middle, and on the right is when going back onto the public internet. So P50 is kind of stable throughout, but P95 and P99, this is where you see a wide variety of latency, and this is what, if I remember my undergraduate economics degree, this is where the margins where you can actually get a lot of economic value. And you can see on the middle that even though there is still some jitter, it's significantly reduced. And so if you're on DoubleZero and you want to land a transaction, you can do that in maybe at the worst about 500 milliseconds, but then on the public internet, it's over a second, maybe a second and a half. And that's a significant amount of time for you to make better decisions. And really what this is all about is having better information, more reliable delivery, so that you can have better economic results for yourself. And so the reason here that this particular RPC provider went off the public internet was because there's an edge case. And this brings us to the next case, what we're going to talk about, which is how do we understand how the network is working? Is it healthy? What parts of the network are degrading? And a global network, especially a decentralized global network at that, is rarely, if ever, fully healthy. There's always some parts of degradation. There's always some parts, some links are coming up, some links are going down, unexpected fiber cuts, and so on. And so this is a way for us to very easily and efficiently see what's going on in the network. And so here you can see, for instance, we have the overview of the links, and we also have healthy drift, telemetry, and missing telemetry, and so on. And we have, looks like, 16 links here that have drift here, which you might think, well, that's not great. But I would actually argue, in fact, that that is very good, because now we have the data to be able to understand that we have this issue in the system, and now we can work with the network contributors to resolve that, and then we can continue to build tooling in that will make these things more easy to understand and easier to resolve. Now, we've talked about things that have existed on the public internet. All the things that I've said so far are existing in the public internet. But let's turn to something else, which is multicast. Multicast does not exist and cannot exist on the public internet. And so we have two case studies here, one with Jito Labs and one with Anza. And we basically have shred stream over multicast and then turbine over DoubleZero multicast. And we're going to focus on the Jito side, but I want to show a graphical representation using real data of what it looks like with turbine over unicast and then turbine over multicast. So here, Frankfurt is the leader. If we click through this, we can see going out to Frankfurt, to Amsterdam, to London. And you can see that this is taking a while. It's going all these different places. And then now it's going to go over to the US and back. And so you can see this is lots of stuff going back and forth. Now, if we look at multicast, this really shows an equitable view of the world. You can see that as soon as a packet goes out, it goes out all over the world. And as we all know, physics can't be beaten, right? So if you're in Frankfurt going to Amsterdam, that's always going to go faster than if you're going to, say, Tampa or Miami. That's just the way that things are right now. So here we have shred stream. So this is the shred stream, architectural overview. You have the Jito Solana sending to turbine, shreds the turbine, shreds the Amsterdam block engine, and these are all over unicast. And these Amsterdam workers are having to basically approximate unicast or multicast rather. And so what happens when you add in DoubleZero multicast is that, as Andrew, our CTO, likes to say, multicast is just a different destination IP. And so here, it's very simple. We just have another place where we send it to, and multicast within the DoubleZero network intelligently replicates this packet throughout and then gets to the other side. And then if we take a look at a higher level, this shows all of the block engines around the world. And you can see the same pattern applies, sending a single packet into that DoubleZero private network, which is intelligently replicated throughout there, and then gets over to the shred proxy on the other side. And we did a test. The test shows that we wanted to measure the difference between the unicast and the multicast thread. And we wanted to make this as simple as possible, so we basically took packet captures and took the timestamps of those packets to measure this. So we measured the difference between the unicast and the multicast packets. So this is kind of a convoluted thread here a little bit. But on the left side, we have Tokyo and we have Frankfurt. And on the right side, again, Tokyo on the top and Frankfurt on the bottom. And so you can see here that there's a substantial increase in millisecond improvements on both Tokyo and on Frankfurt. And Frankfurt even goes up to more than 60 milliseconds. And even here, even though there are some cases where the public internet is faster, we're still getting these P99, P50, or P75, and so on that make it a lot better, where you're much more likely to get this marginal return and potentially a much bigger outsized return than you would on the public internet, this P50 and so on. And then likewise, on the top you have the Tokyo again here, and you can see the percentage of DoubleZero multicast wins over the unicast wins. And likewise on Frankfurt as well. So this shows very clearly that there's a real advantage to using DoubleZero multicast over unicast. And what makes this especially nice is that this is a really simple way for something like Turbine, something like Jito Shred Stream, or any other thing that would benefit from this replication throughout the world to add on, because it's just a different destination IP. And this is technology that has existed for a long time, and that high-frequency trading firms have been using this to reap these benefits for many, many years. And this is something that we value at DoubleZero, and the reason that we've been able to move so quickly is because we're using technologies that have been tried and true and that have existed for, in some cases, 20 or 30 years. So we understand the problem, and we can build a quality system, and one that has been tested by some of the biggest firms and biggest tech companies in the world, and we can bring this into a new way so that people here can benefit from this in a way that wouldn't be possible on the public internet. And so, while physics can't be beaten on DoubleZero, you can shrink the world. Thank you.